Our first speaker is Ronald Prinn. He's the TEPCO Professor of Atmospheric Sciences at MIT in the Department of Earth and Atmosphere and Planetary Sciences, and he's the Director of the Center for Global Change Sciences and co-director of the Joint Program on the Science and Policy of Global Climate Change, or Global Change, and his talk is titled Toward a Comprehensive Earth System Model. Thank you.
Thanks. Okay, now we'll see if the technology works here. Good. I didn't want to see a repeat of what Steve Chu had to do to try to find some of his text. Well, it's a delight to be here, and I thank the organizers for inviting me. I fully agree with Ralph's statement that climate science is already widely recognized as highly disciplinary. But in my case, I've pushed the envelope a little bit further than what most people think of as interdisciplinary. I actually work very actively with economists and people who understand energy economics and also who understand and think about the way future technologies are going to evolve over time. And I think you've got to fold all of those things into the sort of more traditional things we think of as climate, which involve the cryosphere, the atmosphere, the ocean, the land system, and all of the biology in the land and in the ocean are all playing significant roles. So what I'm going to describe as an Earth system model is one that includes humans doing their thing within it and the interactions backwards and forwards. And we've been at this for now 20 years at MIT, and we're only at the beginning. I mean, this is a tremendous task, and I hope what you can take away from what I show you is not that we've got it right, but that we are putting together a methodology for how to do it, and hope that we will get better and better at it over time, rather than to say this is anything near a nailed piece of science. I don't think it is. I think it's going to take another generation. But I'm glad to, myself and my colleagues are glad to have made that first step in what will be, I think, a very long journey. These images from NASA's Terra satellite, let me get them spinning again. Well, they're not going to spin. They are. In an Earth system model, you would love to have a capability to simulate everything you see there. The real image is in the top row in the middle, and then the rest have been filtered to get rid of the clouds and to enhance the view of phytoplankton in the ocean, the changing vegetation over the land, and so on. And the two fuzzy ones, right-hand top, for in the top row and the middle of the bottom row, they are a couple of images of infrared radiation going out to space. So an Earth system model wants to model all of that and wants to do it with perfect accuracy. I say want to, but of course we cannot achieve anywhere near that. But at least we have a vision of where we want to go. And you can't see from the Terra satellite the effect of humanity on this planet. But I think most of us in this room now recognize that those effects are pretty profound. They are not just to do with greenhouse gases and aerosols. They are to do with massive land use change as well, and utilization of the ocean in various ways, and overutilization, pollution of the air, pollution of water. These things are all, in fact, connected together. And in the model that we're put together at MIT, we don't just have the climate components at all. We have a very serious effort in air pollution and the human health aspects of that, and looking very carefully at evolution of land and ocean ecosystems, thinking of new ways in which those can be done better, and bringing them into the system modeling as we see they are beginning to look credible. Why do we need Earth system models? A question everybody should validly ask. One of the reasons that's primary in my thought process is that we do not have another Earth without human influence to calibrate the conflict between environment and development that we surely have today. It would be very nice to have this control experiment as a lab person would have. They would be trying something out, and then they would have another beaker where they weren't trying it out, and they could look at the differences and learn tremendously from a series of well-designed experiments. Well, we only have one beaker, as it were. It's the real planet Earth. So we have to have some numerical simulations of planet Earth that we frankly, and it's it's just one of the unfortunate aspects of doing climate science is we don't have the widely recognized control that scientists usually have. So our control is to simulate the system in a computer, simulate the system as it is existing today, and then we can say, what if we change things going into the future? And what if there were no human influence? We can see how things might vary. As you can imagine, because now it's a computer model, then it's subject to all of the criticisms of computer models. They are imperfect. Their resolution doesn't resolve all of the important things you want to resolve, and I can go on and on and on. In this list in the blue coloring background there are some of the things that are going on in development of the world that are really affecting our environment. Energy is at the top of the list, but people sometimes forget about food and the area of the land that we've taken over for food. The transportation system, the manufacturing system, urban development going on at a tremendous pace in China. Those of you who visited Beijing 20 years ago and then visit today, it's unbelievable what's happened in 20 years in Beijing. Population growth just continues to go up and up. Potable water is getting less and less, and human health issues are getting bigger and bigger, not so much in the OECD countries, but in the rapidly developing countries, where even air pollution takes second fiddle to development. And associated with the development are these environmental issues, and you can make a long, long list. There's climate change, urban air pollution, water quality, land degradation, ecosystem disruptions of a wide variety, and waste disposal. And what's interesting about the climate issue is it does exemplify the challenge for sustaining a habitable Earth, and many consider this to be maybe the biggest environmental challenge going forward. I have a nuanced view of that. I think that it's so closely connected to the air pollution and various water challenges that you can't sort of think of these as apart from one another, but be that as it may. We need Earth system models more obviously, of course, if we want to do any projections to sort of help plan an agriculture and plan an energy system. One wants to have some sort of a reliable system of projecting forward to look at the effects of energy at scale and so on. We became convinced 20 years ago that if you wanted to project climate into the future, you had to couple the natural components and the Earth components of the Earth system together. And this led to what was initially considered an unholy alliance, an alliance between scientists like myself, physical scientists, and social scientists, in particular economists. And I can tell you some of my colleagues at that time at MIT thought I'd gone off the deep end. Some of them still think I'm off the deep end, but I've learned to swim in the deep end, at least, so they can continue to think I'm there, but I'm still surviving. You can look at the climate system and form models, but what you really want to do also is recognize that there's new science, the discovery of new interactions among the natural and human climate system components. Included in our climate system model are various feedbacks, such as when you warm the high latitudes, you increase methane emissions from the wetlands. When you change the hydrology and the temperature of soils, you change the nitrous oxide emissions from those soils. So those feedbacks are already built in to the modeling system that we have, and we've been able to quantify some of those to see, well, how important are they? Some are not as important as you sort of see conjectured in the literature. Others are important. Certainly the methane one is. Objective assessment of uncertainty is really, really important when you're doing Earth system modeling. You cannot believe these models, right? And I spent 2 decades building them. You cannot believe any single run of these models. At best, you can be educated by doing an ensemble of, say, 400 forecasts where you're taking different assumptions in the economics component of the modeling system and in the natural component. Get 400 outputs that you consider have roughly equal probability, and then plot the probability distribution functions of the various outputs. It immediately shows the public that we admit we have uncertainty in projections. And then what we can do, however, is we can take a proposed policy, and that was one of the big reasons for putting this program together, was to analyze policy proposals. And there you compared the risks of dangerous amounts of climate change with and without the policy. And that was the value of the Earth system modeling with the ensemble approach, was that you didn't pretend that you could get the median with high accuracy and then that the uncertainty around that median was very small, and therefore you warmed or cooled the Earth down by that policy by a particular amount, but rather showed what are the odds of, say, greater than 2 degrees, 3 degrees, 4 degrees centigrade warming, and how do you lower those odds when you have a stabilization target, for example. So that's been a big plus of the approach we've taken. And I've already mentioned this, that there are a lot of connections. Climate is not in isolation of studies of air pollution, of biodiversity, one that doesn't get into the news as much as some others. Agriculture is in the crosshairs, as it were, in climate change, and particularly because of water and other issues. Energy, we all know from Stephen Chu's talk last night, energy is right in there. And as we think of new energy supplies, we're going to have to think carefully at the scale of those energy supplies. They look good, a wind turbine, just one of them, but what does 10 million wind turbines look like around the world? And does it have its own issues and problems to be solved? And of course, water quality. So here are the results of, was published in the Journal of Climate in 2009, the results of ensembles of forecasts looking at 4 stabilization targets and no policy. So the top row was no policy. The median in the CO2 equivalents, this is where you combine all of the other non-CO2 greenhouse gases into their equivalent amounts of CO2. Underlying the 1400 is a little around 950 parts per million of CO2, and the rest is all of the very powerful greenhouse gases, industrial gases, that with no climate policy there is no incentive to lower those. Some of them are quite fantastic. Nitrogen trifluoride is an example. It's used in the production of flat screen TVs, and we measure it in the A-gauge network now. It's minuscule concentrations at the present time, but it's growing very, very rapidly. So if you wait for 100 years and flat screen TVs go and continue to use it, then it becomes a very, very powerful contributor to radiator forcing, and so on. So you can see that the stabilization, it goes down to stabilizing at 550 at the bottom. That's equivalent. Currently, most people don't realize how bad the situation is. We're at about 472 parts per million of CO2 equivalents in the atmosphere today. We calculate this continuously from the A-gauge global network for greenhouse gases that I've led since '78. And if you're ever in New York and in the Penn Station area, Madison Square Garden, there's a huge 70-foot sign, and it's showing you the tonnage of CO2 equivalents in the atmosphere going up, clicking up all of the time. And we provide them with those numbers. Each month we update them and give them a projection forward. So 472, and people are talking about stabilizing at 550. Right? Some are talking about stabilizing at 450, but we're already gone by that, and 350. You know, I think that's great if one could ever achieve it, but you know, we do need to be realistic. So what do you see when you look at this? What are the odds of more than 2 degrees centigrade warming between essentially 1990 and 2100, or 2095? Those of you who do climate science, you know you must average over at least a decade or 2 decades to define climate. That you can't take the year-to-year variation as telling you about climate change. But here it is, here are the odds, the black numbers, of exceeding 2 degrees centigrade. With no policy, 100%, stabilizing at 900, 100%, stabilizing at 660, 80%, stabilize at 550, still 25%. The red numbers are where some people calibrate that 2 degrees centigrade warming from pre-industrial instead of from 1990. 1990 is the Framework Convention on Climate Change sort of base year for emissions changes. And so now you see that if you take that as the baseline, that there's 80% chance, even with 550 parts per million as the stabilization level, 80% chance of exceeding the 2 degrees centigrade. That is not going to be easy at all, and we're going to have to be realistic about that. The good news is when you look at any one of the rows now in these projections, so this is 400 projections, so if it's less than 0.25%, it just meant that none of the 400 went above that threshold. So that's what less than 0.25% means. And then you see it's remarkable that although stabilizing at 550 did give you 25% chance of exceeding 2 degrees centigrade, there was less than 1 in 400 chance of exceeding 4 degrees, or 8 degrees, obviously even more so. And that's because of the nature of the shape of the response of the climate system. There are a lot of positive feedbacks that you activate in the climate system that you have to take into account, and we've got a lot of those positive feedbacks in this system. So as you get warmer and warmer, you begin to activate more and more of these positive feedbacks, such as the warming and the melting of the tundra and the emanation of methane from it, and those sorts of feedbacks. So there is some hope that, you know, if you think that 4 degrees centigrade is the threshold, then suddenly, you know, that the tipping point, as Steve Chu used yesterday, then, you know, you might feel very comfortable. But having got you in that comfort zone, I do warn you that this is all dependent upon the modeling system that we have at MIT, and other modeling systems ought to be made and compared. In other words, we can think of this as structural, an attempt in some areas of our model to have structural uncertainty addressed, but it's mainly parametric uncertainty that we're addressing here. So it's the methodology that's important. The general philosophy that we've pushed, that given the uncertainties, we need to evaluate policies based on their ability to lower risk and not to change the median, to lower risk. And by that I mean lowering the odds of obviously dangerous amounts of global warming. 4 degrees centigrade, it means about 8 degrees centigrade of the poles, just to give you a sense of that. And I think most sane people would recognize 8 degrees centigrade warming of the poles. It would take time, but we could probably say goodbye to at least the Greenland and the West Antarctic ice sheet. So certainly 4 degrees centigrade is dangerous. In question time, if somebody wants a rationale for the 2 degrees centigrade that people talk about, I can give one to you quickly, although I don't think it's the official one. Now, let's look at the polar regions now. What's the odds of exceeding 4 degrees centigrade in the polar regions now? This is 60 north to 90 north from the IGSM ensemble. So this was 400, again, from the same 400 in each of these cases. So the 5 cases, there were 400 member ensembles. So you see that the odds of exceeding 4 degrees centigrade with stabilizing at 550 are 0.5%. So 2 of the 400 went above 4 degrees centigrade. Are people willing to just sort of take those sorts of odds? Right? Now, why is this an important threshold, 4 degrees centigrade? It is important because the last the polar regions were about 4 degrees centigrade warmer than they are today was in the Eemian, about 135,000 years ago. And the folk who analyzed the relevant isotopic composition estimate that sea level was 4 to 6 meters higher then in the Eemian than it is today. So forget about models, right? This is a rationale to think, well, there's a threshold. Do we really want to put up with 17 feet or so of sea level rise or get anywhere near the possibility of that? So 0.5% makes you, maybe feel a little bit safe. And of course, these even more dangerous thresholds, 6 degrees, 8 degrees, ones that you see have very low probability. But if I were to stabilize at 660, right, which many sort of feel more comfortable with, under the 660 is about 550 of CO2 and about another 110 of non-CO2 gases, then now you've got 25% chance of exceeding 4 degrees centigrade. And I think now at that point people would begin to be uncomfortable with those odds, because we don't have another planet to go off to. Just very quickly, poles do warm much faster than the tropics. Climate science know why. There's 2 reasons. Low latitudes can export heat to the higher latitudes. The reverse cannot occur. And secondly, there are all these positive feedbacks in the higher latitudes, the loss of summer sea ice in the Arctic and so on. These are all powerful positive feedbacks that are in our modeling system, and part of the reason where as the system gets warmer and warmer, those feedbacks of course kick in and become more and more important. So the Arctic, once it begins to lose sea ice, begins to warm even faster. So 5 meters of sea level rise from the West Antarctic and 7 meters of sea level rise from the Greenland ice sheet is 12 meters. That's 38 feet or so. And clearly we don't want to go there. There are lots of other impacts that people talk about at climate science. I really emphasize this one, because it is fairly straightforward and simple. It isn't such a complex thing. When temperatures go above a certain level, ice melts, and it can have these processes. Those of you who know the West Antarctic ice sheet, it gets hit from above and below. It's grounded below sea level, which is the definition of the West Antarctic ice sheet. And therefore, the warming water penetrating underneath it is equivalent to pushing the ice line, the line denoting the boundary between the ice, the floating ice shelf and the grounded ice sheet moves in that diagram to the left. I've already mentioned this the last time polar regions were significantly warmer. Then we saw the 4 to 6 meters of sea level rise. Ralph mentioned the importance of paleoclimate studies in his short introduction, and I fully agree. We need to push as much as we possibly can to get more and more information about past states, and I would really focus my interest anyway on the warm interglacials, to say what happened in the warm interglacials. There's a tendency to look in the deep ice ages, but we're in a warm interglacial, and it'd be very nice to know more and more detail about what happens in a warm interglacial. There's a huge amount of carbon stored in the frozen soils, stored there through built up through the Holocene. Latest estimate is it's about 1,670 billion tons of carbon. To sort of put that in more human terms, it's about 200 times the current annual anthropogenic carbon emissions is stored there. And if the frozen soils melt, or thaw, whichever term you want to use, then they will come out as methane. As it dries out, they'll come out as CO2. How quickly? We all hope that they'll come out as slow as possible, but I don't think so. So it's another positive feedback. This occurs in the integrated global system model, but we don't have the full extent of how we handle the frozen soils in there, and when we put that in, it's going to make that feedback stronger. We all know, I think in this room, the rather disturbing rates at which Arctic summer sea ice, the sea ice extent at the end of the summer from satellite imagery, that began in 1979, and the red dots are the year-by-year assessments, and this is looking at the percent difference. And it's for the period that you can see there, for 79 to 2009, the rate of ice decrease in the summer has been 8.9% per decade. And you'll recall in 2007, the ice extent was 1/2 of what it was in 1979. I had the, I wouldn't call it a joy, but a privilege of being on the icebreaker Kapitan Klebnikov in the Siberian Arctic at this time, and only 3 days out of the 11 did we smash through ice, whereas in 1979 we would have been having a lot more fun and feeling a lot more comfortable. So that positive feedback is already happening, and it's happening faster than what it is in climate models being simulated. The ocean is very important in the climate system, particularly the meridional overturning or the deep top-to-bottom circulation. It's well known that it's driven only in a few of the polar seas, the tips of those yellow arrows. How can you slow that down? It's very important because it's mixing heat down into the lower ocean and slowing the warming, and equally important, it's mixing carbon, bicarbonate, etc., down to the depths and burying it. It'll come back to haunt us one day, but burying it for the time being, and both of those things are slowing down the warming rate very considerably. So there's concern that it could be slowed down. It's slowed down by decreasing the sea ice in the polar regions and increasing freshwater inputs into these seas. Those of you who have looked at the outputs of climate models, you know that as the seas warm, you get more and more rainfall and snowfall in the higher latitudes that will do exactly that, more freshwater inputs directly from precipitation and from the rivers flowing into the Arctic region. So whoops, what did I do? I thought I was going to have a Steve Shue moment there as well. I was a bit nervous when I saw Stephen do that. I thought, well, he's big time. So what am I going to do? So that's unfortunate. Increased rainfall, snowfall, and river flows, decreased sea ice are, in fact, what we expect from global warming. And this is the model, the ocean model. You can see the grids of the ocean model in the IGSM. That's and that's the bathymetry in the 3D ocean model. But this has been run with a whole lot of scenarios of stabilization of CO2, in which CO2 is increased and then stabilized at the end of 100 years, and then you just look what happens for the next 900 years. Irreversible collapse of the oceanic overturn if CO2 exceeded 620 parts per million CO2 equivalent. That's a model result, so don't write that down and say this is it, that's the threshold, but it does suggest that there is a threshold, and we need a lot more studies as how well we think we understand when that threshold is reached. Because once this collapses, the majority of the carbon dioxide will remain in the atmosphere. There'll be still some taken up by the land biosphere, we hope, and the rate of uptake of heat by the ocean will be very, very curtailed. So it's another thing we're moving into and adding into capability into the integrated global system model is to now look in detail at ocean phytoplankton. And at MIT, there's been a project led by Mick Follows and Stephanie Dudkowitz and others to link a physical model of the ocean circulation that's led by John Marshall's group, and put in the various properties, genetic properties of the various types of phytoplankton, and then see how they evolve over time going forward to see what the winners and the losers are. In the animation you see here, the reds and yellows denote the large phytoplankton, things like coccoliths and so on, and the green and blue denote the small, Prochlorococcus, the one discovered by Penny Chisholm as an example of a small one. Obviously, there's a lot more detail one can put in this, but this is where we're headed, so that we can, in fact, look at the implications of rising temperatures in the ocean and increasing acidity in the ocean on phytoplankton. And this thing that you see on the right-hand side, I won't belabor it because of time, is showing you species by species for the small ones and the large ones what their population was in log 10 biomass units in the year 2100. So this is new frontier work, still lots to be done, but now you can see this is extremely important as well if you want to understand the role of the ocean as a food source going forward, and the continued role of the biological pump in the ocean to help pull CO2 out of the air and so on. How much will it cost? There are not many economists in the audience, but we have a large economics team, and the economics model has many sectors. In agriculture, for example, in crude and refined oil, in the electrical sector, this is just a partial list of all of the sectors that are included. And of course, transport alternatives, more and more are being thought of. And so we're putting these in and try to understand the mix. You always have to be careful when you see an electric vehicle to find out where it got its electric power. If it got it from a coal-fired power plant, you didn't do anything. In fact, you might have been worse off than using, other fuels. So we trace all of that from beginning to end. So we look at, where is the mix of electric power coming from when you have a pure electric vehicle or a plug-in hybrid electric vehicle? Obviously, those are of great concern. We can calculate the policy cost of those various stabilization levels, presuming it's efficient. And that means either a cap-and-trade system or a tax system. All of the rest of the systems you've heard, for very good reasons, cost a lot more money. So when you mandate a technology, like everyone has to have 20% solar power, what you're doing is just saying today's solar technology is good enough, and I'm going to empower that, and off you go. Well, today's solar technology is very expensive. Right? So at that point, there's no incentive to invest by just simply saying it's got to be that percentage, so it turns out to be a lot more. But here it is. This is welfare loss, and welfare in economic terms is the total consumption of goods and services, or it's a very good measure of it, in a country. That usually rises over the multi-decade time period, about 3% a year. About 2% of that is due to innovations and so on, and the 1% is due to population growth. So 3% is 1 year's growth of consumption of goods and services. So that's a threshold that you could look at and say, do you surpass that threshold with these stabilization levels? Well, even at 550, there's only 10% chance of passing that threshold. Right? This presumes great efficiency in the way it is, and that it's an international policy. So clearly, those are odds I think that people are worth, would say that's worth it to do the 550. And it would mean if you did have the 10% did occur, that you would wait a year to get the same consumption of goods and services. As we went into a recession, we've somewhat seen, the growth, of course, go down very substantially. But this is quite different. This would be happening slowly, year by year. So, in fact, you would hardly notice this. And there's only 10% chance of exceeding that. I'm going to finish up with saying a little bit about the scale of the challenge to transform the global energy system. Stephen Chu mentioned this, but I'm going to put it more in the context of a global look. Right now, 87% is coal, oil, and gas of energy consumption, and it's about 400 exajoules per year is the total global energy consumption. And the tops of the gray panels that you see here, across the tops of the gray bars, they represent the energy demand if there were no policy. If we just simply went blindly ahead, energy demand would grow and it would be satisfied in various ways. The challenge now is to say, what if we wanted to go to 660 parts per million as the stabilization target? I'm not recommending that one. You can tell most of us would rather have the 550 if it were at all possible. But let's look at 660 and see what happens. Well, one of the biggest things that happens, and it's driven by an increasing cost of carbon or carbon equivalents. The carbon price in 2100 is $1,750 per ton of carbon. Steve Chu mentioned $20. He didn't say per ton of carbon, but I think he was referring to that. And that would be the beginning cost, and it would just grow over time. And so efficiency gains are a big player in this, both in buildings and in transportation. There's a lot of waste of energy. This assumes that there's no nuclear, that it hardly grows at all. So biofuels, Stephen Chu mentioned this. Biofuels come in as replacements for the liquid fuels that are coming from the dwindling oil that you see that's there. And these are driving transportation in this new system. It assumes for the biofuels that they, from cellulosic material, that the chemists have worked out how to convert that into sugars and alcohols and various fuels. Nuclear was deliberately restricted. Coal with carbon capture and sequestration plays a big role, and you can see the dwindling of coal, oil, and gas over that. If unrestricted, nuclear competes with and could replace coal with carbon capture and sequestration. A lot of us were very enthusiastic or optimistic about solar. I still am, by the way, because I think the way that the wake-up call that we've got from Fukushima is going to people are going to look very, very, very carefully at why did it happen and what can be done to shore up the defenses of the existing power plants and how to build them even better. So I don't think nuclear is off the table, but I think it's going to be slowed down in the near term because of that. If I wanted to grow that much biofuels, and this is where the business of scale is important, you need an area of cropland which is about 8.5 times the total U.S. cropland to give that global production that I talked about. It's not all going to be in the U.S., of course. The land in the U.S. is too expensive, so it'll go into the cheap lands that are arable. Arable meaning it gets enough rainfall. So here it is, a projection in the economics model, coupled with the land system model, to look at, where would biofuels be growing in the year 2100 in that scenario I showed you. Red pixels have 80 to 100% of the pixel is devoted to biofuels. So you can see areas like this one in Africa. Africa, by the way, finally gets something to export that's worth a lot of money. But you look at this, and there are big issues. Competition with food for land and water, greenhouse gas release during land conversion, the loss of natural ecosystems, the tropical forest, and the climate effects themselves of the land conversion, the change of the hydrologic cycle. These have got to be sorted out before we go in that direction. I was going to say something about wind. I'm going to speed it through this very fast. Two issues for wind. At the scale that of, say, getting 10% of global production in the year 2100, you have to have about 5 million wind turbines, and we put all of these in semi-arid cheap lands around the world in the land. And you get warming of the surface because you're basically stagnating the lowest 100 meters, 150 meters. The wind shear that normally drives the turbulence that cools the ground is a lot less. So you get this warming effect, and so that sort of tells you have linear arrays of the turbines perpendicular to the winds and don't put them downline in the wind system. But even more important, perhaps, is the intermittency. Even if you average the wind availability over the whole of the North American continent, there's a factor of 2 change over the season. So that means you have to have backup, huge amount of backup. Steve Chu mentioned batteries and things like that. That's money. So when you speak backup, it's money. A lot of people are talking about climate adaptation in addition to climate mitigation. I think we all agree, certainly given the fact we have no policy right now, that at least we can talk about adaptation. And I don't think that to this group I have to point out the importance in adaptation of having a very accurate forecasting model for water availability at the regional level and so on. Where not there, we would have wheels, if you like, or odds being shown at the regional level that would have such wide range of possibilities that they may not be particularly good for planning at the present time. Lots of people are now in desperation talking about geoengineering. It is true that you can, by putting reflectors in space or in the stratosphere, you can reduce the incoming solar light to mimic any of the stabilization levels that I talked about. So for the 550 part per million, I can reduce solar radiation linearly, increasing that reduce from 0 now to 2.5% by 2100, and I'll get the results of warming that look very, very similar to 550 part per million stabilization. So you can do that. But then there's the problems. Shading does not prevent the decimation of the carbonate shell phytoplankton. The CO2 levels would continue to rise. My joke is, of course, to solve this problem, we could add sodium hydroxide to the global oceans or genetically engineer new phytoplankton. And there are sure to be unintended consequences leading to international conflict. Kevin Trenberth and his colleagues did an interesting study of looking at the rainfall change during the Pinatubo incident, and rainfall lowered by a significant amount. No surprise, less sunlight at the surface, that's what drives the hydrologic cycle. That's an unintended consequence because that was not good for agriculture. So this is the final set, really. To summarize, the research challenge. I think this research challenge for going forward is the most difficult, most interdisciplinary, yet maybe the most important systems problem that faces the world today. We need to, in doing this, couple the natural and the social sciences and the engineering sciences together, and people have got to learn to communicate better and better. We've made a start of that at MIT, so we can, we can talk about it and how difficult it is and how easy some of it is and how more difficult it is in other cases. But we're a long way from the perfection that's needed. The scale problem is a really important one. If you talk about wind and biofuels and solar and so on, you've really got to look at the thing at the scale of producing, say, 5 or 10 terawatts of energy in 2100 and ask what the planet looks like, right? And what other things you've got. And I used the lesson of the chlorofluorocarbons. Ralph, of course, knows that one very well. Beautiful invention in the 1930s of Midgley, and the perfect refrigerant, right? And at very low scale of use, no problems, and then everyone began to use them, not just for refrigeration, but for aerosol cans and so on, and we all saw that, and fortunately were able to nip it in the bud. We can use a thought process and an Earth system model to prevent creating industries that would then later on have to be disbanded, right? We can look ahead. The educational challenge is a huge one. We're looking at this at MIT, and I know other universities are. We've got to have our students be able to cross disciplinary lines and at least learn what's going on elsewhere, and improve communication. So this is the way we communicate uncertainty and the danger to the general public, and it seems to work very well. And we have real physical versions of these wheels. The one on the left-hand side, it shows you the odds of no policy, the results that I showed you before, and these are the odds of getting various amounts of warming, global warming. So you see that 25% odds of getting greater than 6 degrees centigrade global warming, that's 12 degrees or more polar warming. Those of you who know about the Arctic know, well, that's it. The Arctic just won't be there under those circumstances. It'll be evolving rapidly into something else. And then the 660 parts per million is the one on the right. And it looks so much less risky to spin that wheel. So we use this, and this is the wheel we are spinning now. We're not spinning the one on the right-hand side. We're nowhere near heading towards that. We are literally spinning this wheel on the left-hand side. These wheels, by the way, are in Monaco. The Prince of Monaco wanted a couple of the wheels, and he's put them at the entrance to the big ocean museum there. So in the city of Gamble, this is called the greenhouse gamble. People can spin these wheels and form their conclusions. Thank you.